Hey guys, welcome back. So today we're going to be looking at something called components of vectors. All right. Now, last class we were looking at adding vectors together, and if you did the exercises, you would have come across an interesting exercise we did. In fact, the last exercise. We were adding together two vectors just like this. So we were using the chain method or the head to tail method. And so we just make this long chain. And these two vectors, we'll call this one A and this one B. It turns out that they were at right angles to each other, right? So this is a right angle right here. And so when we have these two vectors at a right angle, we can add them together and we're going to wind up getting a resultant that looks something like this, right? Something like that. So this resultant we'll call R. And because these are right angle vectors, we're actually able to directly compute certain values about R. We no longer have to resort to a measuring tape and measuring experimentally the length or the angle with a protractor, right? So the idea here is that R is equal to A plus B. And we're actually able to get the magnitude of R by calculating it directly. When we recognize a right triangle, we can use now Pythagoras, the Pythagorean theorem, where A squared plus B squared equals the hypotenuse, C squared, right? So here the hypotenuse is R, and so this is going to be equal to the square root of A squared plus B squared. So we can directly compute the magnitude of R. We no longer need to use a measuring tape. Likewise, if we define an angle here and call that phi, then we can also calculate phi using trigonometry. Now that we have a right triangle, we can use trig. So in this case, we have A and B, and so we know that tangent of phi is going to be equal to the opposite over the adjacent. And so in this case, the opposite is going to be the magnitude of B, and so then divided by the magnitude of A, and so you'll get tangent of phi. So if you want to, you can just solve for phi, and that's going to be the inverse tangent, or the arctangent if you want, of B over A. And there we go. So we're able to directly calculate now the magnitude of R and the direction of R, because we have this unique, well, not unique, we have a special case with a right triangle. So right triangles are really interesting for us. With right triangles, we're sort of able to have this special case where we can directly compute the resultant's magnitude and direction. And that's really good because we don't always want to be using a protractor and ruler to try and add vectors together. It's better to do things mathematically if we can. So, great. That's nice. But so what? Well, here's sort of the genius move. Instead of looking at two vectors we add to get a resultant, what if we try and reverse the process? Okay, we're going to do it backwards. So this is the idea. What if we do this backwards? Right? So now the idea is we're going to take any vector and we're going to break it into these kinds of components. And we want these components to be at 90 degrees to each other, so we create these right triangles. But more than that, we want these components to be parallel with our axes. Okay, so they're going to lie on the axes in in that orientation. So let's see what this is going to look like. Let's imagine we have a set of x and y axes, just like this, okay? So here's our x-axis and here's our y-axis. Now what we can do is we can define some random vector, something like this. It can be anything really. And we'll call this our vector A, okay? So it's just an arbitrary vector. What we're also going to do is we will define an angle, okay? So let's define this angle as theta. So theta is going to be the vector direction from the positive x-axis, okay? So it's just going up from that positive x-axis at an angle of theta. Okay, good. Now, if this is true, then we should be able to decompose this vector A into x and y components, just like this. So what I'm going to do is I'm going to call this side here, I'm going to call this A sub x. So it's the x component of A. And then I'm going to look at this side. And here we will have what we'll call A sub y. So the y component of this vector A. This is going to be very, very useful. Now, how can we actually figure out what A sub x and A sub y are? Let's look at A sub x first. Okay, so we've got this x component of A. Is there some way that we can calculate how big that is? Yes, there is. We can use trigonometry because this is now a right triangle. And so we have an angle we define as theta, and we know that in this case, A sub x is the adjacent side, and this side, the hypotenuse, is magnitude A. So we can say that the cosine of theta is equal to the adjacent over the hypotenuse. Just like that. And so if we want to solve for A sub x, well, A sub x is then going to be A cosine theta. Voila, we have the magnitude of A sub x here. Likewise, we can do the same thing for A sub y, and that's because this length here is actually A sub y, right? This is the same magnitude, even though here it's on the y-axis. We can see that these are going to be the same lengths. So we can see that A sub y is actually the opposite side from the angle theta. And so opposite over hypotenuse is going to be a sine of theta. Solving for A sub y then, we're going to see that A sub y is equal to A times sine of theta. And so here we are. We're able to use this angle theta to create x and y components of any general vector that we're calling A. This is really good. Now I do want to point out one thing here, and that's that these components are technically not vectors. Okay, so right now these components only have a magnitude. They are a scalar. In the future, we will find a way to create vectors with them, to make them into vectors. So right now we're drawing little arrowheads on them, but that's just sort of out of convenience. They're not actually vectors yet. We'll get there soon, okay? But we don't need them to be vectors right now. Okay, so we can create these components. What can we do with them? Let's try and do some calculations. Okay, so now we're going to look and see how we can use these components in calculations. Now I'm going to bring back this little graph that we drew before with the components and this vector A because it is beautiful. Now, what can we do with this? Well, we can use this now. If we have the components, we can treat this like the exercise that we did in the previous class. And that is we can use these components to reconstruct vector A as well as its magnitude and direction. So let's do that. What we see is that we're going to use Pythagoras, because this is a right triangle, right? And so we can find the magnitude or length of vector A, and that's going to be a sub x squared plus a sub y squared, and then we're going to take the square root of all of that, right? So this is the Pythagorean theorem. So if we have the components ax and ay, we can reconstruct the magnitude of the vector A, which is just any general vector. Of course, the other thing that we did in the exercise last class is we found the angle theta that's the direction of vector A here. And we did that using tangent, right? So tangent of theta we know is equal to the opposite over the adjacent, right? So here's theta. In this case, the opposite side is here, and here is the adjacent side. So this is going to be equal to a sub y over a sub x. And of course, we can then calculate that theta will be equal to the inverse tangent, or arctan, of a sub y over a sub x. And so this is a way for us to calculate the magnitude of A as well as its direction, theta. So it's really good. If we have components, we can get the original vector back, no problem. However, there is actually a little problem here, and that is when we're calculating theta, we have to be careful. Why? Why do we have to be careful? Well, because we're using tangent. Okay, now let me show you something that's a little bit annoying about tangent. Okay, so what I've got here is a graph of tangent. This is the tangent graph. And what you can see is, it has this swoopy shape here. And between negative 90 degrees and 90 degrees, we sort of have this continuous curve. And then after 90 degrees, between 90 and to 270, this curve shape, it repeats itself. Okay, it repeats itself. Now, this is not super surprising, right? If we draw, for example, a sine wave, sine waves repeat themselves as well. But for the first 360 degrees, the sine wave shape doesn't repeat itself. It repeats after 360, right? For tangent, it's different. It repeats every 180 degrees. So here, this separation between this distance rather, is 180 degrees. And that can be an issue because in a full circle, we have two 180 degrees. We have 360 degrees. And so tangents repeating itself like this introduces a problem for us. Let me see if I can illustrate what this problem looks like. Let's delete this here. Here's the problem. Let's say I have a set of axes, okay, and I have some vector here, and let's say that this angle is 30 degrees, okay? What is the tangent of 30 degrees? Well, let's get our calculator out here. So 30 degrees, and the tangent of that is going to be 0.577. Okay, 0.577. Great. No problem. So that means if I was here calculating ay over ax, and if ay over ax was 0.577, right, I could take the inverse tangent of 0.577, and I would get, here it is, let me do it, the inverse tangent, I would get my 30 degrees back, okay? 30 degrees. Well, that sounds great. Where's the problem? Here's the problem. Let's say I have another vector over here, okay? And here I have an angle from the positive x-axis all the way here, and this angle is 210 degrees, okay? 210 degrees. Well, what is the tangent of 210 degrees? Let's see. 210, and the tangent is 0.577. 0.577. 7, 7. Now do you see what the problem is? Now, if I have some value from ay over ax, and it's 0.577, and I take the inverse tangent of it, my calculator is going to give me 30 degrees. But actually, it could be 210 degrees. Why? Because it could be 30 degrees or 30 degrees plus 180 degrees, which is 210, because tangent repeats itself after every 180 degrees. So what this means is, when we do the inverse tangent of ay over ax to get our theta, we don't know exactly what quadrant this theta is in. It could be in quadrant 1, or it could be in quadrant 3. It could be flipped 180 degrees, right? It could be in quadrant 2, or it could be in quadrant 4, flipped 180 degrees. We don't know unless we actually draw a sketch. So the lesson here is that you must draw a sketch of your component vectors like this to see exactly which quadrant your resultant vector is going to be when you add them together. So that's the warning. Okay, the warning is that tangent is annoying because it repeats every 180 degrees instead of being a nice function like sine or cosine that doesn't repeat until after 360 degrees, which is fine. We only have 360 degrees in our circle around the axis. So sine and cosine are great. Tangent's a little bit annoying. All right. So that's the warning here about tangent. What else can we do with this? Well, we can also use components to help us multiply a vector by a scalar. Okay, let's see what I'm talking about. Well, let's say we have a scalar c, and we're multiplying it with a vector a, and we're getting out some vector d. Okay, well, what can we do here? Let's draw some axes so we can have a little picture here, and let's draw a vector a, something like this. Okay, so here's our vector a. There it is. Okay, what if we want to multiply this vector a by 2? Okay, so what if we want 2 times vector a? How can we figure that out? Well, one way is to, graphically take this a, copy it over, head to tail, make a chain of 2 of them, and you can measure that up. Okay, yes, we can do that. If we know the magnitude of a, it's just 2 times the magnitude of a. But let's say we know the components of a. Okay, so let's say we have this component here, and we also have this component, the y component, over here. Okay, so this is a sub y, and this is going to be a sub x. Well, what we can do is we can now multiply the components by the scalar. Okay, so what we're going to do is we're going to multiply this scalar times a sub x, and we're going to multiply it by a sub y. So now, what is that going to look like? Well, here we have this, and I'm just going to eyeball this. But if we double a sub x, it's probably going to look something like that. Maybe a little too long. Something like that. Okay, that's pretty good. And a sub y here is going to get doubled to about there. Something like that, right? Now, what we can do is we get a little ruler out. We can try and see where this is going to wind up. Something like this, right? So now if I draw my vector 2a, that should look something like this, right? So now this is going to be my vector 2a. And we can see that that lines up, right? So by doubling the components, we're actually doubling the length of vector a. And so we can multiply the components by a scalar, and that will be the same as multiplying the vector by the same scalar. Okay, so this is sort of our lesson here on how we can multiply scalars with vectors and use components to do that. So in this case, in general, dx would be equal to c times ax, and dy would be equal to c times ay. Okay, so this is sort of the rule here about how we can multiply vectors with scalars and use components to help us do that. Great. Okay, let's do one more thing with components, and that will be to add vectors together. Okay, so now we are going to be adding vectors with components. How do we do this? Well, let's draw some axes. And we're going to draw a vector A plus a vector B, and that's going to give us a vector R, some resultant vector. Put that in green. Okay, and we're going to draw this using the chain method, the head to tail method, and also show how the components line up. So give me a second here and I'll draw this out for us. Okay, so what I've drawn here is the chain method showing a vector A plus vector B becoming this resultant vector here in green. And what I've also drawn is underneath it, I've shown here's A sub x and here is A sub y. And then I've essentially added on B sub x onto this length and also B sub y onto that length. And what we can see is that they sort of add up to become R sub x, and this winds up being R sub y, which lines up to become the components of this final resultant vector R. So the general rule here is that when we're adding vectors together, R sub x is going to be equal to the sum of A sub x plus B sub x, and the same goes for the y components right here. So if we have components, it becomes a very easy way to add the components together, and that's the same as adding the vectors together. We'll get the same exact resultant. Very, very useful. And this can be useful when we have lots of vectors, right? So when you have many vectors, then maybe you have a situation where you have a vector here, and then a vector here, and a vector here, and a vector here, and a vector here. And then you need the resultant vector, which is something like this, right? Well, in this case, you can add up all of the components all at once, where Rx is going to be equal to A sub x plus B sub x plus C sub x plus D sub x plus any other vectors that you're adding on. And the same thing will go for R sub y. And so this is an easier way to add many, many vectors together, because all of the y and x, all of the y components are in a line, all of the x components are in a line, so you can just add them all up together, right? If you didn't have components, it would be really tedious to try and calculate how all of these long chain of vectors add up together. Components serve as sort of a shortcut for that. And one last thing I want to mention is that this also works in 3 dimensions. Okay, so far we've been on the XY plane stuck with 2 dimensions, but actually this kind of situation works well with 3 dimensions as well. So let's draw us some X, Y, and some Z axes like this. Okay, let's say we have some vector A that's going to start here And let's say it winds up over here. Okay, so let's say that this now is vector A, and let's see how this falls onto our axes here. Let's say it falls out here, right, with some x, y, and z components like that. So this is x, this is y, and this is z. Well, what we can see is, we can define these lengths as our x, y, and z components. So we can define this length here to be a sub x, right? This is going to be a sub y, and then this would be a sub z. And a sub z. And so three-dimensional vectors can also be broken down into x, y, and z components. And in this case, the magnitude of this vector A is going to be equal to essentially the Pythagorean theorem in 3 dimensions. So it'll be ax squared plus ay squared plus az squared, and all of that will be the square root. And so that gives us now the magnitude of a 3-dimensional vector A. And so just to note here, if we're going to be using 3 dimensions, in this case, we would wind up having an r sub z, and that would be equal to, a sub z plus b sub z plus c sub z plus d sub z, and so on and so on. So 3 dimensions work equally well when using components like this, and it's really going to help us out when we do future calculations. So if you have any questions about components, please leave a comment down below, and we're going to have some exercises for you to practice. You can download them, find a link in the description below for a link to a PDF on my website, some exercises that you can do. And if this helped you out, please give me a like and give me a sub. It really helps me out, and I'll see you for our next lesson. Thanks a lot. Bye-bye.